Mass spectrometry and atomic mass. A mass spectrometer can be used to determine the relative abundance of the isotopes of a substance. The atomic mass of a specific sample of an element will vary due to the relative abundance of each isotope present. The mass spectrometers measure the mass-to-charge ratio of charged particles like ions. The symbol for mass-to-charge ratio is m/z, since the symbol for mass is m and for charge number is z. In this course, the charge number for all ions entering a mass spectrometer is taken to be 1. That will simplify the analysis. The AP exam does the same thing. Since z is equal to 1, you will see the horizontal axis measured either in m/z or m. Even if the axis is labeled m/z, only m will be measured in units of AMU, since z is presumed to be 1. How does it work? The sample over here is ionized. It is made into charged ions by being heated with the filament. The now ionized sample is accelerated into a magnetic field. Based on where the ion hits the detector, the relative mass-to-charge ratio and abundance of each ion can be determined. So here's your magnet, and here's your detector over here, and here's your display. When a charged particle, like an ion, shown down here, travels through a magnetic field, it is deflected into circular motion. In a mass spectrometer, each ion enters the magnetic field, and that's the green dots, which tell you the direction the magnetic field is coming out of the page. They each enter the field with the same velocity, so their deflection depends only on their mass, since we are assuming z is equal to 1. The larger the m/z ratio, or charge to mass ratio, the larger the circle, and the farther away the ion strikes the detector. Here, m, this guy here, has a higher mass to charge ratio than little m, so is detected farther away from its point of entry. So you have your detector over here. Okay, so this is the little m, hits it right here, and the bigger m hits it farther from where the ion came into the magnetic field. The idealized mass spectrum of a neon sample is shown below. For each peak, A, B, and C, the height on the y-axis is proportional to an isotope's abundance, while its position on the x-axis gives its mass. The peaks are not exactly to scale, so they can be more easily seen. Analysis of this mass spectrum display yields these data. Peak A has a mass in AMU of 19.99 and an intensity of 100.00. Peak B, mass in AMU of 21.99 and an intensity of 10.22. And finally, peak C, mass of 20.99 and intensity of 0.29. The mass spectrum intensities are then converted into the percent abundance of each isotope. Using this equation here, the intensity of the isotope divided by the total intensity gives us its percent abundance. The total intensity was adding the three intensities up, and we got 110.51. Then you put in the intensity of each isotope, divide, multiply by 10 to get a percentage, and you get the relative abundance here, which adds up to 100%. And finally, we use these data to calculate the atomic mass of neon, which is the average mass of the isotopes weighted by their abundance. So neon 20, okay, so here's 100 divided by 110.51 to find its percentage, and that's 90.50%. Neon 22, and this is we're just taking from the previous slide, right? We found these three percentages, and they added up to what? They added up to 100%. So here's the first one, neon 20. The atomic mass unit's 19.99 times 0.9050, 0.905. Then we took neon 22, and here's its percent abundance, 0.0925. And then finally neon 21, that's the least of all of them, so that gets weighted the least, right? Because there's only 0.25% or 0.0025 of it. Add them together and we get 20.18 AMU, atomic mass units. And that's the mass you see on the periodic table. Often, as in our example so far, the mass spectra are presented as relative intensity versus mass divided by charge, m over z. Sometimes a percent relative abundance versus m over z is used. Either graph can be used to determine the atomic mass, as shall be shown in the next couple of slides. Here we have the percent relative abundance, and we have two peaks. Okay, one is at 10 m over z, the other is at 11 mass over charge. Here's their percent relative abundance, and let's see, you'll see that they add up to 100%, which is good. So the atomic mass that will be shown on the periodic table, we have 19.9 times 10 plus 80.1 times 11, right? That's the atomic mass of that, the mass per charge. And then we have to divide the whole thing by 100, and we get 10.8 AMU. And now we have percent relative intensity, and the first thing we have to do is add up the two intensities, and what do we get? 100 plus 23 is 123. So for mass 1, which is a charge to mass ratio of 10, the percent abundance will be 23 over the total, 123, and that gives us 18.7. For isotope 2, we have 100 over 123, and that gives us 81.3. To find the atomic mass, we multiply 10, that's the charge to mass ratio of the first one, times 0.187, plus 11, that's the second guy here, times 81.3. Add them together, and we get 10.8 atomic mass units.